Good morning, Algebra 2ers. Hope you guys are doing well. Today we're going to be starting a new section of material that kind of goes through and ties together all of the different ideas that we've covered so far this year. So if you look in your binder, this will be maybe right around page 263. And the letters that we're choosing to use here, MT1, just stand for Midterm Review. And we are just smushing together everything that we've covered so far this year. Okay? We're going to be doing some solving, some graphing, identifying key features, and identifying function types. Okay? So it's really a big picture view of everything that we've covered. So if we look at the first few questions here, the first side of the notes, it says, give the name of each type of function, then solve the equation. So if we go ahead and start with number 1. Let me zoom in here. We have 2 plus 4, and that's in front of this group x plus 9 all squared, and we're equal to 10. So if we are wondering what type of function this is, having something that is squared means that we are dealing with a quadratic. It is a quadratic that's in vertex form. It has a grouping with it, which would tell us direction instead of the ABC type of quadratic. Now, in this problem, we are solving since we have an equal sign. And if we go ahead and we try to solve this, the first thing that we really need to get rid of is this pesky 2. It's pretty easy to move. If we go ahead and subtract 2 off of both sides, remember we have to do the same thing on the left and the right. So we have 4 times x plus 9 as a group squared, and then 10 minus 2 is 8. I'm sure you can see probably what needs to go next is we're going to divide by 4. You cannot take that 4 and distribute in. That would be an incorrect step. And the reason that is because the exponent is more power in this case. It is being controlling, the group here, x plus 9. So now that we've canceled out the 4's, 8 divided by 4 on the right-hand side is just equal to 2. And so I have x plus 9 all squared equal to 2. And you can kind of see that the exponent is the biggest issue here. How do we get rid of an exponent of 2? Well, it's fairly easy if you use a root, which is the chapter that we just gotten done completing. So square rooting the left and square rooting the right. Okay, square root of 2 doesn't break down. If this were like a 20, we would try to factor tree that. But 2 is a prime number, so we're just going to keep it as square root 2. This is roughly 1.4142, but it keeps on going. So it's not a nice looking number. Root 2 is just a little bit better. And then you have to remember if we get absolute value bars here or not, okay? Having a squared inside, you can square positive things inside. You can square negative things inside. Both of those things are squareable. And so because we can start with positives and negatives, and it's okay, we are going to get absolute value bars. Maybe I want you to see the difference that if this was a square root inside and then we were squaring, you really can only square root positive numbers. And so that's what I'm looking at here to determine if we get absolute value bars. Essentially, the x plus 9 is what's left over when those things cancel, but because we can have both positives and negatives, we have absolute value bars around the x plus 9. And in order to get rid of those, not too hard, I usually will scribble those out, and then we put a plus or a minus sign on that other side. And so x plus 9 could equal positive root 2, or it could equal negative root 2. Those are my two cases. And now getting rid of that 9 is as simple as subtracting again. Just remember, when we subtract and we have a plus-minus version, those two different possibilities, if you will, the minus 9 or whatever the constant is that we're moving over has to go in front of your adding and subtracting sign. So here we are at the end. X is equal to negative 9 plus root 2, and then negative 9 minus root 2. If I were to ask you how many answers that is, that would be 2 answers, which all quadratics have 2 answers. go ahead and let's take a look at question number 2. This problem seems kind of similar, actually. It's 2 plus, and we have 4 in front of a square root. X plus 9 is underneath that square root. That's the radicand, and that's equal to 10. So actually, first step would be exactly the same. We've got to subtract 2 from both sides. So if we go ahead and do that, leaves 4 times the square root of x plus 9. And that's equal to 10 minus 2 is 8. From here, we can go ahead and we can divide by 4, canceling those things out. And so you'll notice some parallels across these two problems. Here we have the square root of x plus 9, and 8 divided by 4 is equal to 2. Now, how do we get rid of a square root? That's really the thing keeping us from getting x. Okay, we can't subtract 9 because it's inside the root. So getting rid of a root is as easy as taking it to that power. So square roots to the second power. Cube roots here would be to the third power. Fourth roots to the fourth power. So we have to do that to both sides. Luckily, we just have one item that we are squaring. If we had multiple things here, we would probably have to FOIL. But now, do we get absolute value bars in this case or not? We're starting off with the square root here. Square rooting things wants to be square roots of positives only. If we take square roots of negatives, that's not good. Those would be imaginary. When I go ahead and do this next step of writing out x plus 9, I do not need absolute value bars. So if your square root is inside, it's only the positive case you want to consider. If you're squared, your power of 2 is inside. There are 2 cases, positive case and a negative case, because you can square positives and you can square negatives. Let's go ahead and we'll get x plus 9 there on the left, only the positive case. And then we're equal to 2 squared, which is 4. Now we can go ahead, subtract 9 and subtract 9. And then 4 minus 9 leads me to be in the negatives. X is equal to negative 5. There we go. All right, so actually very similar work between these two problems, step by step, but there's kind of a difference here in the middle of when we get a plus or minus versus just plus. Okay, and so that's something to really know. Let's go ahead and let's take this over to question number 3. All right, question number 3, different format. Ooh, I forgot to label the type of question here for number 2. Let me go do that real quick. Question number 2 here is a square root. I may have said it at the time, but I don't know if I wrote that out. So make sure that we're labeling what we're dealing with. That's a good review. Okay. We'll get to number 4 here in just a second. But if I go back to question 3, it looks like I was dealing with x squared minus 6, and that's equal to 16. Because, again, it has a squared in it. Even though it's got 3 pieces, 3 terms, this is still going to be a quadratic. Quadratics have a variety of formats that we can deal with. And so the first thing that I really need to probably do here, since it's an ABC quadratic, is to get all the pieces together. And that means moving the 16 to join the fun over on the left-hand side. Okay, if we can get it to be all together, we have a variety of tools that deal with ABC quadratics. So x squared minus 6x minus 16, that's equal to 0. You could do the quadratic formula. You could maybe do completing the square. If you do that, remember you just have to move the c back over and divide this in half. The kitchen tools, when we talked about that during that chapter, would be the things you're remembering here. I like to factor. I think that's the fastest way to deal with ABC quadratics, and usually they will tend to work out because we've set them up that way. So here for the x factor, you take a, which is 1, times c, which is negative 16. That answer goes in the top. The b value, which is right there in the middle, goes in the bottom. Is it possible to multiply to negative 16 and add to negative 6? I think some combination of 8 and 2 can probably do that, but the 8 has to be negative. 2 minus 8 adds to that bottom number, while they both multiply to the top. Then you take the a value, which is 1, and that's what we divide by. So these two sides tell me my two groups. I take x minus 8 as a group and multiply it by x plus 2 as a group. And if I FOIL those things out, I get right back to that ABC quadratic form. So setting that back equal to 0, we have kind of a cool property that says if I multiply to 0, this group has to equal 0, or potentially that group has to equal 0. And so knowing that, what minus 8 would make 0 for that group? X equals 8, 8 minus 8. What would make this second group 0? What plus 2? Well, if you started off as negative 2. Okay, and having both of those possible numbers, either one makes my product 0 out. So if you remember some of the steps that we've done a long time ago and kind of how to wind your way through a problem, there's not a lot of work sometimes that goes into it. Okay, but you have to remember these steps, and that's why this target is tricky. Let's take a minute to look at number 4. Okay, number 4 has this weird, yucky exponent. Okay, it's a fraction. And if you remember the name for things that are fractions when we studied the fractions chapter, that's called a rational. So this is a rational problem. This is a rational exponent. Okay, if you thought about what those exponents mean, dividing by 2 means that that's really a square root. So you could call this kind of a square root. The inside would be cubed. So there's a lot of variety of ways that you could maybe talk about this, but in this format it has a rational exponent. It's a rational problem. Now, the problem here is still getting inside to x. We want to solve for x here in a second. So the first thing that's easiest to move is this 2. Always get rid of adding and subtracting first. So what I'm thinking about is PEMDAS, the order of operations, but to undo it, going backwards up the order of operations. So get rid of adding and subtracting first is easiest. That was that step. Okay, so we have 4 times this group, x plus 9 to the 3 over 2 power, and 18 minus 2 is 16. Okay, here we go. With the 4, do not distribute in. The exponent is controlling the group. You get rid of a 4 by dividing by 4. That cancels those things out. So you'll notice now I'm doing multiplying and dividing. I'm moving back up the order of operations. X plus 9 to the 3 over 2 power. I'm leaving a little bit of extra space because I'm going to need to get rid of that exponent here in a moment. But 16 divided by 4 is 4. Okay? Now you can kind of see that I'm going to have to deal with the exponent next. How do I get rid of an exponent of 3 over 2? Now back in the fraction chapter, we got rid of that exponent by putting brackets around this. There's nothing special about brackets. It's the same idea as bigger parentheses. But we raised this 3 over 2 exponent to its inverse power, which is 2/3. Exponents raised to exponents, remember, we multiply those. And if we specifically choose 2/3, 2 and 2 will cancel, 3 and 3 will cancel, and now that exponent is 1. It's gone, essentially. It cancels out. Now, whatever we do to one side, we have to do to the other side, and so we're going to raise 4 to the 2/3 power. So now that we've had the exponents cancel, put little cancel marks there, we have x plus 9, and that's equal to whatever this is, okay? So 4 to the 2/3 power. Okay, usually the inside number here will be a kind of a nice number to maybe cancel out the exponent. And as I'm looking at this, actually I'm kind of noticing that 4 is equal to 2 squared. Okay, and so we would change it to be a perfect number, but this is still raised to the 2/3 power. Okay, so nothing actually cancels. And in fact, you'd multiply 2 times 2, the numerators together, to get 2 to the 4/3 power. Okay, and what does that mean? What does that look like? Okay, if you don't like this format, you could really think about this more as a root, which is fine with me. Dividing by 3 means this is a cube root. Inside we have 2 to the 4th power. Okay, so this might look a little bit better if we take 2 to the 4th power, which is 2 times 2 times 2 times 2, meaning 16. Can we deal with the cube root of 16? That's pretty easy. If we break 16 down, we get 4 times 4, and each 4 is another 2, 2, 2, 2 pair. And this really changes if we group them out to be one group and one left over. That's what 4/3 would be. It's one whole and then one more left over of a third, being how many you would need. So if I wrote that right-hand side in root form, cube root form here, 2 cube root 2, that doesn't look too bad, okay? Usually we will put numbers in here that cancel out fairly nicely, but for the notes we didn't. Now, how do I get rid of the 9 here and get only x by itself? Well, I need to subtract 9, okay? Subtracting that 9, be careful. You cannot put it with any of this. This is a very particular decimal amount. And so what we're going to do is we're going to subtract 9 just afterwards, okay? You could also put minus 9 in front if we want, so I'll give you two varieties of answers. X is equal to 2 cube root 2, and subtract 9 off of that total. Or if you wrote out x is equal to negative 9, notice the minus is still in front of the 9, and then we go ahead and we add, since this is positive here, 2 cube root 2. Both of those are the exact same answer. I might tend to lean with the first version just because it seemed a little bit more natural as we were going, but the second version is fine as well. So hopefully those 4 questions gave you a nice variety of problems to look at. And we're going to maybe step away from solving on the front page and look more at graphing here on the second page. So let's go ahead and let's flip over. Okay, so on page 264, if we look at the instructions, graph the function, then identify the key features. So we're going to be ending up over here with this key features table and talking about the different qualities of our graph. But first we have to see the graph. Okay, if we look at question number 5, overall, this particular type of function is a quadratic. It's got a squared in it. Okay, so that's the first thing that I am thinking about. Quadratics, if we remember, are a U shape. So having something that's a squared ends up kind of as a U. And so we need to really talk about some of the qualities of this U. Being ABC format doesn't tell me a lot. I know that we are reflected. And actually, when we're in ABC form, this C constant, this little baby at the end, is going to be my y-intercept. But there's not much else that I can know about this. It is useful, actually, for quadratics to view them from several perspectives. And so if we take this quadratic and we factor it, if we x factor, we're going to see different perspectives on how it would work. So let me go ahead and let me put a little note here that we might want to x factor, question mark. And if you recall, x factoring with negatives in front, not usually the best thing to do with the x factor. It kind of breaks down a smidge. So if I divide everything by a negative and flip all of my signs, so if something was negative, like minus 15, it becomes positive. If it was plus 8, it becomes minus 8. Dividing that negative out leaves me with a quadratic that is a little bit more factor friendly. If I set the x factor up, I might be able to view this from the perspective of groups and talking about its x-intercepts. So y-intercept, very important. X-intercepts, very important. Okay, so inside here I have 15 and negative 8. If I try to multiply to 15 but add to negative 8, negative 5 and negative 3 both fit the bill here. So I really have x minus 5 as a group, x minus 3 as a group, but you have to remember this negative trails along, and so I am still reflected with those two groups. Now, why did we do this? To figure out that x equals 5 and that x equals 3 are both x-intercepts. If you are a solution, you are an x-intercept. And so a couple things that we could kind of say here. Okay, I'll make my pen a little bit bigger. 5 as a value happens right here. 3 as a value happens right here. My y-intercept as a value happens somewhere down here. Okay, so it continues off the grid from what I can typically see, just in my 10 by 10 by 10 window. Now if we're going to go ahead and draw a U in, I would like to try to be as accurate as possible. And so if you remember that this U shape is symmetrical, the vertex, the turning around point of this U is going to happen right at 4. So we have a couple of options, okay? Figuring out where its height is not too hard. We just have to use x equals 4, and we plug that in for each x value, and we solve. So I could do that in ABC form, or I could do it in grouped form. Both of them give you the same answer, but I would like to know where the center point is. So looking at this, negative 4 squared, and then plus 8 times 4, and then subtracting 15 off of that answer, leaves me with negative 16, plus 8 times 4 is 32, and subtracting 15. If I subtract 16 away from 32, I have 16 minus 15, and so the answer, which is really the y value here, is 1. 4 as an x value goes with 1 as a y value. That's 4, 1. The reason we do that is to know kind of the relationship that these points are going to have. If this vertex point maybe was moved up a little bit, maybe it was scooched up here, it had a height or an answer of 2, well then I would know my a value is 2. Now, one thing that you will be able to tell is in ABC form here, this number with the x squared is always going to be the distance between these 3 dots. Okay, so the fact that it's negative 1 kind of tipped me off that it is going to be 1 unit away, right there where it was sitting, 4, 1. But that's something that we needed to review. So from here, if you remember, quadratics and their U shape have a special pattern of 1a, 3a, 5a, we can get a lot more points out of this, and it just keeps going by the odds. And so a here equaling negative 1 tells me that I can go 1 times negative 1, that's that gap. 3 times negative 1 is the next gap, so I have a point here and a point here. That's 3 away from the prior point. And then 5 times negative 1, so out a little bit. 1, 2, 3, 4, 5. All of these points are x values that I could test and do something very similar. I could just keep making an xy table essentially. But if I look at where my my y-intercept will be, this was 3, then 5. If I count 7 away from 8, 7 away from 8 lands me at 15. And so that's where this further down point is. And if you want, you can go ahead. It goes through all of these points. It's actually really hard to graph and video at the same time. So there we go. That's our picture. Now let's go ahead and let's talk about some qualities of this picture. Okay, some of the work that we've done earlier is actually going to pay off here, because when I talk about my x-intercepts, well, I've already found them when I found the solutions. So I can go ahead and just put 5, 0 and 3, 0. If we are doing a shape that kind of naturally crosses the x-axis, so I can just look along here, and anywhere along that x-axis I would put points that are on that location. My y-intercept is that point that's way down there, and so that would be at 0, negative 15. That's the constant, the little baby at the end of the bus. My domain here, where does it live in this horizontal direction? Where are its x values? And so it keeps going left forever, just a little bit at a time. It also keeps going right forever, just a little bit at a time. And so this is going to be a function whose domain is all reals. It goes from negative infinity to positive infinity. After that, the range, the y values, I'm looking down and up for its heights. And so this graph does not go up forever. There's actually kind of this natural ceiling, if you will. No floor, goes down forever. So negative infinity. But the cap of this function, the highest it will ever go, is at 1. And I need to put a bracket there because that's its maximum height. You'll never get answers that are above 1. 2 as an answer is an impossible answer. Now after this, it's been a while since we talked about positive intervals, but intervals themselves are x values. They're amounts of time, snippets of your x-axis. And if you remember positive, it just means above the x-axis. That would maybe be an okay note to write down. I told you that this is kind of like flying an airplane above the water. You have positive heights. And so the only case where that happens is in between these two x values. My graph is above the x-axis during those moments of time. And so I need to start at an x value of 3, and I need to end at an x value of 5. It's only for 2 seconds that we're an airplane, really. Now, what about the negative interval, which is kind of the opposite case of being below the x-axis? Well, early on in the graph, from negative infinity all the way up until that x-intercept, we are negative. We're a submarine. Okay, submarine here, submarine here. Okay, so we would want to write that from the beginning of time, from negative infinity, this graph is going to be below the x-axis until it gets to 3. Now, actually, from 3 to 5, we are above. We're an airplane. But then at 5 seconds, we switch over again, and we're a submarine for the rest of our lives. Okay, we are below from 3.1 to 3.2 to 3.3 as x values, all the way out forever. So we would go back to this box, and we say from 5 seconds in time to infinity seconds in time. Awesome. So there we go with the positive and negative intervals. Those are usually fairly easy because they're based on your x-intercepts. So these two things tie together. Hopefully all that made sense. It's a lot to go back over, but it's things that we've done. So that leads us to the question given below this. Using the function, using the graph above, or the equation above, find the average rate of change over 0 to 3. Okay, 0 to 3 here, both being x values. X equals 0, x equals 3. Tell us where to start looking and where to stop looking. What is the average rate of change? Now, if you remember, average rate of change is really just the slope of this graph. So can I find the slope of this u from 0 to 3? Now visually, 0 here is at the point 0, negative 15. It helps to have some of this table filled out because sometimes they give you free bonus points. 3 as a point actually happens right here at that x-intercept. So 3, 0. So I don't have to do any work to find these. Now, if I needed to, just like earlier when we found 4, 1, okay, when we found this point, you can always plug in an x value and do the work to get the answer. That is perfectly fine. Sometimes we'll give you things that you haven't actually found or used, and so that's going to be the strategy I would try. But using these 2 points, if you recall, these are x1, y1 for our first point, x2, y2 for our second point, and average rate of change was delta y over delta x. It is the rise of your function over the run of your function. That's what slope is, rise over run. The little formula that goes with this is y2 minus y1 over x2 minus x1. Okay, having delta y, delta means the change. And so we're finding the difference between those two y values and the difference between those two x values. So it's as simple as just putting these different numbers in. y2 is 0, subtracting y1, which is negative 15. Notice I'm subtracting a negative. On the bottom, x2 is 3, so I'm dealing with this right now. And I'm subtracting x1 right here, which if we go over is 0. So 0 minus a negative 15 makes positive 15 because we just subtract a negative, it makes a plus. And that is over. 3 minus 0 is 3. 15 divided by 3 is equal to 5. So what we're saying about this graph is that the slope to get from this point here to this point up here is 5, or 5 over 1. So let's travel like that. Down here at negative 15, I travel up 1, 2, 3, 4, 5. I land at negative 10, and I go over 1. Okay, I'm not there yet. I've just started the race. If I go up 1, 2, 3, 4, 5, and over 1, not there yet, but I'm getting close. Up 1, 2, 3, 4, 5, and over 1, and that fits perfectly from start to finish. That is the slope between those two values. Hopefully that kind of connects it in visually. All right, let's go ahead and let's move on to number 7, and let's see how this particular function works. Okay, we have t of x, good old Timmy here. It looks like I'm dealing with a square root. Just like on the front, it is helpful to label the functions that we're dealing with. So this square root function I know is going to be an arm with a very special pattern that's related to quadratics. 1, 3, 5, 7, 9. The odd numbers are hidden inside of that, since square roots are kind of like the cousins to quadratics. They're related. Now, a few things about this particular square root. We are reflected. Actually, just like the graph above has that negative and this was reflected, we have a 3, which in this case is a stretch, a vertical stretch. Plus 8 is going to move us left 8, it's backwards, and then plus 6 is up 6. Hopefully this one is pretty easy because we just got done doing a whole section on these particular types of graphs. So let me put some of these points in. Okay, going left 8 and up 6, that is where my new vertex is going to live. Okay, we start here. Okay, this is a single arm, so I don't have anything to the top left, or anything going to the left, I should say. Negative and a 3 tells me that I need to step down 3 before going over my pattern. Okay, we always go over 1 for our first distance. Now I'm going to go down 3 more, and now I need to go over the next number in the pattern, which is 3. Down 3, over the next amount, which is 5 away. So I'm saying, oh, look, I'm 4 to the left. 5 more from that would be 1 over on the other side of the y-axis. Step down again, 3 units. And if we've done 5, that means the next distance here is 7. 7 away from 1 puts me at 8. And if I could step down 3 more and go out 9 more units, and I'd be somewhere right in this neck of the woods. It keeps spacing out further and further and further. So from this starting point, I can go ahead and I can try my best to make it through all of those different values. Actually, I might try a little cheat. Wasn't bad. I'm going to scooch it around here just a smidge. Okay, take your time. Doesn't have to be perfect. Okay, but technically all of these points are connected. The curve goes through all those points. Put your arrow on the end. There's nothing to the left. This is a square root, which they don't work for negatives. Those would be imaginary for our graph. Now we can go ahead, we can fill out our table of key features. Let me see if I can fit both on here. Okay, so x-intercept. If we kind of look across the graph for where we cross the x-axis, that happens right along here at -4, 0. Okay? So we don't have to solve with this one. Square roots really don't have a lot of forms. They just have that one form. So the graph gives me this information. Now, the y-intercept, you notice it's not in my key features table. If I look along the y-axis, I'm crossing at a location that is not a nice whole value point. And so we didn't feel like it was the easiest to find that. You can always find the y-intercept if you set x equal to 0 and put 0 in. So you get the square root of 8, -3 times the square root of 8 plus 6. And figuring that out is why we get a decimal value. It's not very nice. It's not very friendly. Okay, so the next thing we're asked to find here is our domain, the x values. This does not go left and right forever. It stops out here at -8. So -8 is almost when it's born, if you will. It goes to the right forever and ever and ever, so we'll go out to infinity. But -8 as an x value is the last acceptable x value to put in. If I put -8 in, -8 plus 8 makes 0. And square rooting 0 is really the first real number that's square rootable. Now the range, the y values, its heights. Because it's going down forever, because it's reflected, it will continue that way. So from -infinity, it keeps going, keeps going, keeps going, keeps going. But we hit this natural cap here at this height of 6. So 6 is the highest answer that I will ever get out of this. And that happens actually when -8 plus 8 is used, making 0. Square root of 0 is 0. -3 times 0 is 0. And then you take 0 plus 6. I'll never get an answer of 7. That just doesn't happen. An answer of 8 never happens. Okay, so those are impossible heights, impossible answers. So here for increasing intervals, we didn't do that on the first one, but that would be like going up a roller coaster. So if you go back to the very first chapter, these were when I gave you some of these hints. And if I get on this graph and I continue to the right, I'm not going up a roller coaster ever. And so what we could say here is just none. Don't leave it blank, because then I don't know that you understand that it's never increasing. What we have here is a problem that always goes down the roller coaster. If I start at -8, I'm just going down, 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 down for the rest of time. And so remember, intervals are x values. So starting at -8 and continuing on forever, that says to the right towards infinity. And now, what do we need to put around the -8? Okay, this is kind of a tricky idea, but we are going to end up putting a parenthesis there, and here's why. -8 itself, that point, I don't know if I'm increasing or decreasing. If I just gave you this point and I zoomed in, if I just zoom in at this point, am I going up here? Am I going down here? Well, you don't know if you're going up or down because it's just a singular dot. It's the fact that when you start to connect it to other dots, oh, now I know I'm going down. Or, oh, now I know I'm going up, because you have dots connected to dots leading you to more conclusions about things. So singular points themselves cannot be included inside of increasing or decreasing interval. Okay? So endpoints here don't mean anything. Let's go ahead and let's go back and talk about positive intervals. So the positive interval here, where I'm airplane, starts at -8 as its x value, and it goes until that x-intercept at -4. So this little strip of the x-axis, I was positive. Before -8, the graph just didn't exist. Okay? So we can start at -8, and we finish right there at -4, excuse me. We cannot include -4 as a point, and that is because that has a height of 0. 0 is not a positive number. Okay? Now, what do we put on -8? Being as we just got done talking about how -8 has to have a parenthesis on it, this is going to be a hard idea that -8 for a positive interval actually is a point that is positive. So this end point, if I just put a dot up here, that point is positive in its height. If I put a dot down here, that point is negative as its height. And so points, if your end point is above or below the x-axis, they can be included in your intervals. And so I actually need to put a bracket around -8 because that point itself is an airplane. Okay? I cannot include -4 as a point because that point itself is neither positive nor is it negative. It's not above the x-axis, nor is it below the x-axis. This point is excluded. So my negative interval picks up at -4, and it continues for the rest of time. So -4 is the odd duck out. It's a boat, if you remember my analogy. Airplanes and submarines are separated by boats. So from x being at -4, can't include -4, but then going for the rest of time, this graph is a submarine. All right, all of those things are things that you need to kind of think through if we give you a question like this. And that's really it, guys. So I hope that going through these variety of questions, reviewed the materials from this year, nothing's really off limits. And so you need to go back and reference some of those notes and reference older chapters of things. That's a good way to remember what we've taught you and remember some of the different techniques that we've tried throughout the year. So hopefully this video helped, and I will see you guys soon. Take care, everybody.